Good day, engineers. I am proud to share this beam calculator web app I made that can solve the reactions, shear, moment, slope, and deflection value of any beam and automatically locate the point of maximum deflection. This can solve multiple non-prismatic spans, and you may add internal hinges at any joint. So I made this specifically for my structural theory students for demonstration purposes only. So it may not provide the exact values for complicated beams, but nevertheless, it provides results close to the theoretical values. Note that some errors in shear and moment ordinates might result from distributed loads being added over long spans, but you may verify the values using the solved reactions, as this application uses a Hermite cubic field for the displacement and rotation. So let's go ahead and open our beam solver. This is our user interface. So we can try to model this beam. For the spans, separate the distances by commas. So we have 6, 2. And then for the modulus of elasticity, the default is 100. This is so that you can obtain results in terms of EI. And I per span is 10 times e to the minus 6, but the unit is meter to the 4. And then I per span is by default 10 e to the minus 6 m to the 4. This is equivalent to 10 million mm to the 4. Then for the global elements, this is the division per segment. So you may increase this value to get closer to the exact results. Then you can also check exactify outputs to bring the values closer to the theoretical values. Now for the joint supports, we have a pin at A and a roller at B. But in the application, I am using only 2 degrees of freedom. So we have joint 0 and joint 1. We cannot add roller supports. As substitute for roller supports, just add a pin support. This is so that no eggshell deformation is permitted. So we will add our pin. Then at joint C, this is essentially joint 2, joint 0, joint 1, and joint 2. We have no support there, so click on none. Now onto the loads. We have 50 kN per meter applied from 0 meters up to 6 meters for the first span. So let's change this to 50. Then the end load is 50. If ever there are changes, for example, we will use 50 and 10, this becomes trapezoidal. So again, we have 50 and A is equal to 0 and B is equal to 6. So from 0 meters to 6 meters of the first span. Then let's add our point load. We have a point load at joint C. So this is 45 kilonewtons acting downward. By default, positive is downward. So if you have an upward load, just add a negative sign. This will become upward, as you can see here. But let's change this to span 2. Then this is applied 2 meters from point B. So let's make this positive again. This will act downward. And then our pin supports are automatically added. So click on compute. You can see the reactions. We have 135 and 210. Then for the shear values, these are the actual shear values. 135 and 165. So there is some error there. This is 134.6 and this is 164.6. This is due to the approximation by the cubic field. So you may just verify the values using the actual reactions that are solved in our beam sketch. Then for the moment, the maximum moment is 182.25. This is very close to the theoretical value. And then for the deflections, the deflection we have solved, the maximum deflection is 642.65, which is this ordinate. And we can see the location here. The maximum deflection is at 2.876 meters from the left, and this is the value. So what we have solved here is 2.87555, which is 2.876. So this locates the maximum deflection, and then at this particular point, you can see the ordinate from the overhang. So the deflection at the overhang is 420 kNm cubed over EI in terms of EI. So we can also see that value. And then the slope at 6 meters is 270. So in order to analyze the slope at 6 meters, since the ordinates here are for the maximum ordinates, we have a point evaluation function. You can just input the value of x. So the roller support is at 6 meters from the left. So just input 6. And then this is from span 1. Then click on compute. Then click on probe results. We can see the slope and deflection. So the slope at 6 meters is 0.27. Multiply this by 1000 to convert back. Then you will get 270. Now we may also try a fixed ended beam. Let's use this example. We have a span of 6 meters. So 6, and then let's make this 10. For the supports, we have fixed at each joint. The 2 supports are fixed. And then for our load, we only have a triangular load from 0 up to 10. So click on this. Our starting load is 0 going to 10, then applied from 0 up to 6 meters, the full span. Then we click on compute. We will obtain the following values. So the reaction at A is 9 and the moment reaction is 12. Then you can check the direction here, counterclockwise. 12 counterclockwise for the moment. And then at joint B, we have 21 for this reaction, and then the moment reaction is 18. Now there is some discrepancy because we have changed our global elements to 1000. Then the maximum deflection is at 3.148 meters from the left, and the value is minus 16.958. So if we will try to check, the one we have solved is 16.958. Now this is close, very close to the actual value since there is no presence of internal hinges. Then the location is at 3.1482. So it is also very close to the actual value, 3.148. Here we have 3.1482. So this can solve multiple spans up to any degree of indeterminacy. And the main advantage is you can also solve non-prismatic beams. So that's it for our demo. Just visit our page in case we have new updates, and I will just provide instructional materials. You may access this free beam calculator on our website, cboardexamgenerator.com.